Hello. Today we're going to talk about the extreme value theorem. We've already spoken about Lagrange multipliers at this point, and we're going to see how they are helpful in finding extreme values on closed and bounded sets. So here is the formula in all its glory. Let f be a continuous function of two variables defined on the closed and bounded set S. Then there exist points. You've got x sub capital M, y sub capital M, and x sub lowercase m, y sub lowercase m in S, such that f of the capital M point is the maximum value of f on S, and f of the lowercase m point is the minimum value of f on S. So basically this is saying if we have the graph of a 3D function, if we only look at that graph on a bounded region, so it's not open, it's closed and bounded region, then there's got to be a maximum value over that region, and there must be a minimum value of that region. And basically you have two options for where those extrema could occur. They could either occur on the boundary, and that's where Lagrange multipliers are going to help us, or they occur within the interior of the region. And that's where we'll make use of the second derivative test. So we're going to get ready to see an example of how to do this. Of course, there's also an analogous theorem for functions of three variables, but for right now we'll just work with functions of two variables. So these are the steps that we're going to make use of to maximize and minimize the function on S. First of all, we'll find the stationary points and other critical points of f by taking the derivative, finding out where it's equal to the zero vector and where it's undefined. We'll only care about the critical points that are actually in S. If they're outside of our region, then they're irrelevant to the situation. And then we'll evaluate the function at each of the critical points that is found in that previous step. So we can see how large it gets at each one of those critical points. Is it a maximum? Is it a minimum? Is it a saddle point? Then we'll use the method of Lagrange multipliers to locate the points on the boundary of S that maximize and minimize f. So subject to the constraint of the boundary, what is the maximum value of the function? What is the minimum value of the function? We'll evaluate the function at each of those critical points on the boundary of S, and then we'll compare all the extrema that we find from steps 3 and 5 to find the maximum and minimum values for the function. So whatever the largest function value we found on either the interior of the region or the boundary, that would be the maximum value over that closed bounded set. And whatever the smallest value that we find, either on the boundary or inside the region itself, that would be the minimum value of the function over that closed and bounded set S. Our first problem we're going to tackle using the extreme value theorem is this one. Find maximum and minimum values of f of xy equals x squared plus y cubed on the region x squared plus y squared less than or equal to 4. Now, if you are familiar with your algebra and how it relates to geometry, you should recognize that region as a circular region centered at the origin having a radius of 2. We're going to try to determine where this function, f of x, where does it reach the maximum value above this circle, and where does it reach the minimum value above this circle? And that could occur somewhere in the interior of the circle, or it could occur on either of the boundary points. So we're going to follow the steps that we talked about on those previous few slides. First step, since f is a polynomial function, the only critical points are going to be stationary points, right? There's no weird points that are going to show up, or we're going to have sharp points or anything. This is just a polynomial. It's x squared plus y cubed. So we're going to need to look at the gradient of f and determine when that is equal to the zero vector. So the gradient is also very easy to calculate. The partial derivative with respect to x is 2x. The partial derivative with respect to y is 3y squared. We have both of those listed here. We need that to equal 0, 0. So the system of equations you get from this is actually very easy, right? 2x equals 0, which says x must be 0, and 3y squared equals 0, which says y must be 0. So the only solution to this gradient equation is when x, y is the point 0, 0. That is the only solution. That is also in the interior of the region of interest, right? X squared plus y squared equals 4 is the graph of a circle with radius of 2 centered at the origin. We just found 0, 0 as a point of interest, as a critical point, as a stationary point, and 0, 0 is inside that circle, so we will keep that point going forward. Now, before we evaluate what it's equal to in comparison, we're also going to take a look at our boundary function. X squared plus y squared equals 4. Using Lagrange optimization, we need to rewrite this as x squared plus y squared minus 4. We'll call that our function g of xy. And then we'll need the gradient of g, which is going to be partial derivative with respect to x for the x component, 2x, and the partial derivative with respect to y, 2y, for the y component. And we set the gradient of f equal to lambda times the gradient of g. Here is our gradient of f, here's the gradient of g. From this, we get two equations, and our boundary equation yields the third equation. And again, I'm going to turn off the video so we can get the use of the full screen going forward. So we see our three equations. 2x equals lambda times 2x, right here. 3y squared equals lambda times 2y, it's the second equation. And then the boundary, x squared plus y squared equals 4. Notice I no longer have less than or equal to 4, because we're only caring about the boundary, which is when it equals 4. From the first equation, we get two solutions. Either lambda is equal to 1, because then you'd have 2x equals 2x, or x is equal to 0, then you'd have 0 equals 0. We can then take those two solutions and find out something more from the other equations. For instance, if we take x equals 0, we can plug it into our constraint equation to find out what y is equal to. When x is 0, y must be either plus or minus -2. So we now have 2 points of interest, x equaling 0 and y being -2, or x being 0 and y being +2. Those are two. But let's go back to the other situation. We said that lambda could also equal +1. Well, if lambda is equal to +1, then we should be able to find a relationship about y. 3y squared would equal 2y in that case. And we can move 3y squared equals 2y. Here we have it. If we move the 2y over to the other side and factor, you would have y times 3y minus 2 equals 0. Thus, y is equal to 0, or 3y minus 2 equals 0. Solving for y tells us y equals 2/3. We already had 0 as a point of interest, so y equals 2/3 we need to explore as well. Right, we had negative. I take that back. You'll have to pardon me. Excuse me. We had x equals 0 earlier. We now have y equals 0. If you plug that into the constraint equation, you get x equals plus or minus 2. So we have -2, 0, and 2, 0 as other points of interest. So now we need to evaluate the function at 0, -2, 0, +2, -2, 0, and 2, 0. Lots of different points. And then we also need to pay attention to 2/3. If y equals 2/3, we can also do substitution into the constraint equation, do a little algebra. If you want to pause the video and make sure you can do it, the algebra should suggest that x is plus or minus 4 square roots of 2 over 3. So we have 2 more points of interest given here. So now that we've found all the points of interest, the stationary points and the critical points on the boundary, we need to evaluate the function at each of those points of interest to find what's going to be the maximum and what's going to be the minimum. So if we plug 0, 0 into the function, we get 0. If we plug 0, negative 2 into the function, we get negative 8. 0, positive 2 gives us positive 8. Negative 2, 0 gives us 4. Positive 2, 0 gives us 4. And either one of these square roots, the positive or the negative one, when plugged in with the y value of 2/3, will produce 104/27. So by the extreme value theorem, the maximum value over this region must occur at either a point on the boundary or in the interior. We've found all the interesting points at which that could possibly be. Therefore, the maximum value the function reaches is 8. And the minimum value the function reaches over that region is negative 8. You can do a little arithmetic here on your calculator to verify that 104/27 is smaller than 8. So maximum value is 8. It occurs at the point 0, 2. Minimum value is negative 8, and it occurs at the point 0, negative 2. I think it would be useful to also examine the graph of what's going on here so you can picture it better. Remember, we're looking for f of xy. Where is it largest and where is it smallest over this circular region? So I have taken the liberty of already graphing x squared plus y cubed. It's the surface. You'll see a red circle on the graph. That is the graph of x squared plus y squared equals 4. So it's down on the xy plane. And then there's a yellow curve, which is the graph of the circle as it intersects with the surface. So you can see on this side we do get a highest point, and down here we get a lowest point for this surface. Kind of looks like a chair of some sort. And this is the point that we'd found earlier. This is 0, positive 2, positive 8. Maybe if I turn it this way. And this is 0, negative 2, negative 8. And so the points do match up. The algebra matches up with the geometry as we would expect it to if we did everything right. It's pretty cool to be able to see the graphical representation showing us that what we had done algebraically does prove to be correct. And that's where we're going to end this video.